This is Eliquis, a blood thinner that made over $13 billion in revenue for Bristol Myers Squibb in 2024. It's the highest earning of the oral anticoagulants, a class of drugs that prevents blood clots, and a class of drugs that has origins as a rat poison. Or at least, that's a story I'd heard for years, but never fact-checked. So for this video, I looked at how scientists found these earliest anticoagulants, including the rat poison one, then how newer generations of blood thinners got popular, and finally, how these blockbuster blood thinners made so much money that the US government got involved. But before we get too deep into the story, we need to start with the basics. How does blood form a clot? Alright, so high level, blood is made of red blood cells that carry oxygen, white blood cells for immunity, plasma to act as a medium for all the sugars and proteins floating through circulation, and these little cell fragments called platelets. Whenever there's an injury that severs a blood vessel, those platelets clump around the injury and plug it up so the body doesn't bleed to death. But to stabilize that plug even more, the body kicks off a complex series of chemical steps called the clotting cascade, which results in a substance called fibrin. This fibrin, along with some other materials, binds the platelets together even stronger, which forms a clot. It's a great response to have if you don't want to bleed out every time you cut yourself shaving, but that same clotting process can cause problems too. Like when a clot forms in a blood vessel and blocks blood flow, it's called a thrombus. When that thrombus moves elsewhere in the circulatory system, it's called an embolism. If a clot forms in or lodges itself in the blood vessels of the brain, it can cause a stroke. And if it gets stuck in a coronary artery, it can cause a heart attack. These thrombotic events are super common causes of death, so cardiologists care a lot about clots. Now, scientists knew the basics about platelets, fibrin, and the clotting cascade back in the late 1800s, but there was a lot they didn't know. And that brings us to William Howell, an American physician-scientist at Johns Hopkins studying how blood coagulation worked. In 1916, he had a student named J. McLean study a substance found in dogs' brains that supposedly sped up blood clot formation. It was a waxy white powder they called cephalin. Seth referring to the brain. So they prepared a bunch of similar extracts from dogs, cats, and ox brains and hearts, and when they tested them, it seemed like they'd be good coagulants. Blood that wouldn't clot in 30 minutes on its own only took a minute to clot with cephalin. But certain preparations had the opposite effect. They actually prevented blood from clotting. Just a few drops of certain extracts could keep blood from clotting for over 6 hours. One of their most interesting anticoagulants was a chemical isolated from the liver, which we'll come back to. But in the meantime, Howell and McLean published their first round of findings in the American Journal of Physiology as the thromboplastic action of cephalin. After publishing, Howell took on another student, and in 1918, they isolated a different anticoagulant from the liver that they called heparin, hep meaning liver. Confusingly, Howell published an extraction method for a different substance a few years later that he also called heparin. The first one was fat-soluble, the second one was water-soluble. Either way, it was mostly crickets. Heparin didn't have a big impact on medicine at first. The method they used for extracting heparin yielded a product that was too impure and in too small of a quantity for human use. So heparin would need to be more pure before it could be useful. Coincidentally, it was one of the discoverers of insulin, Charles Best at the University of Toronto, that decided to tackle the refinement process starting in 1928. This resulted in the crystallization of heparin sodium, the version of heparin that went into production thanks to the university's partner lab, Connaught Labs. In 1937, Best and his colleagues published another paper. This time they showed that injections of heparin could prevent blood clots in dogs. They'd also been conducting human trials too, and they'd already shown that it was generally safe during surgeries. And the timing couldn't have been better, because this new and improved heparin came out a few years before the invention of a bunch of new surgical technologies, including one of my favorite pieces of medtech, the heart-lung machine. See, if you were a heart surgeon doing a coronary artery bypass in the 1950s, it would be easier to operate if the heart weren't beating. Doctors could use different chemicals to stop the heart, plus ice to slow down the body's oxygen consumption, but they would have loved a way to pump oxygenated blood around the body while the heart was stopped. So researchers and engineers in the 50s came up with machines that would take deoxygenated venous blood, add oxygen, then pump that blood back into circulation. But when they started testing these new machines, the blood would clot in the tubes, which would clog up the machine and make it useless. But with the right dose of heparin, the blood wouldn't clot, and oxygenated blood would flow indefinitely. So heparin made the heart-lung machine possible, which made more precise open-heart surgeries possible. And from there, heparin settled into its role as a surgical drug, like when inserting stents or during organ transplantation. That made heparin the first in a class of drugs called anticoagulants, or drugs that prevent blood clots. You could also call them blood thinners, but that term also includes antiplatelet drugs like aspirin, plus another one that I'll talk about in a few minutes. Also, side note, I saw a few articles mention that the term blood thinner is kind of a misnomer. Anticoagulants don't make blood less viscous. They don't change blood from syrup into water. They create blood that doesn't clot as easily. It's more like turning it from chunky peanut butter into smooth, except the peanut butter is liquid. Right, so doctors learned pretty quickly that heparin wasn't absorbed when taken by mouth, so it would need to be given via injection to be effective. But it wasn't until the 1970s that scientists learned how it worked. It all came back to the clotting cascade. Scientists learned that this original unfractionated heparin binds to an enzyme in the blood's plasma called antithrombin, which gets the enzyme to change shape and boosts its ability to inhibit thrombin. It also inhibits activated factor 10, or factor XA in Roman numerals. The result is less fully formed thrombin, which produces the fibrinogen that turns into fibrin, which prevents clots from forming as easily. Now, heparin was great for surgeries, but it couldn't be taken by mouth. And the search for the first oral anticoagulant finally brings us to our rat poison. But first, I want to preface this section with a disclaimer. When people tell this story, they usually cite a 1959 article in the journal Circulation written by Carl Link, who will become relevant in a second. He opens the story with, quote,
"Like any good story, it need not be told in exactly the same manner each time. In Wisconsin, it's become kind of a legend. I shall consider only the high watermarks of certain chapters."
So I've tried to pull other sources when possible, but the main beats are still the same. So then, in the winter between 1921 and 1922, there was an epidemic spreading through the cattle in the prairie land between North Dakota and Alberta, Canada. These were sometimes violent death where the cows would bleed to death internally. So initially, veterinarians thought it might be sepsis caused by some kind of bacteria, but on dissection, they couldn't identify a germ that could cause the infection. But then, a vet working in Canada noticed that the dead cows tended to eat the same thing: sweet clover hay that had gone moldy. As a result, the bleeding disease earned the name sweet clover disease. The vet published his initial findings in 1924, but the epidemic continued. So in 1931, he teamed up with an agriculture expert in North Dakota, and they showed that you could control outbreaks in two ways: either by getting rid of the moldy hay or by giving the cattle blood transfusions from a healthy cow. So you might think, lesson learned, there's something in the hay that made cows bleed to death, so avoid sweet clover at all costs. That is not what happened, because now we're getting into the Great Depression, and with limited resources, some farmers didn't really have a choice but to feed their cattle whatever hay they had. One of these farmers who'd lost a bunch of cattle to disease was a Wisconsin farmer named Ed Carlson. So one night in February of 1933, he drove almost 200 miles to Madison through a blizzard with 100 pounds of sweet clover and a container of very liquid, not coagulated cow blood. Carlson showed up to the office of a biochemist named Carl Link at the University of Wisconsin-Madison. This guy is our main source for the story. Link thought it sounded like sweet clover disease, but his only advice to the farmer was to stop feeding them the bad hay and give the sick cows blood transfusions if you could. But Link's curiosity got to him. He and his colleagues tested the blood and couldn't get it to clot at all. So Link, his lab mates, and his students spent the next 6 years trying to find and isolate the chemical that kept the blood from clotting. And in 1939, one of his students found it. They found that the mold changed a naturally occurring chemical called coumarin into the chemical that caused the bleeding. It was called dicumarol. The next year, another student synthesized dicumarol in the lab and patented the process on behalf of their funding organization, the Wisconsin Alumni Research Foundation, or WARF. A few different companies got FDA approval for dicumarol in the mid-40s, and some of the early studies had promising results for dicumarol as a therapeutic. Like in 1947, a research group led by Allen published a paper showing that out of 329 patients with pulmonary embolism treated by heparin and dicumarol, only one patient died. And according to stats in the 1940s, untreated pulmonary embolism had a mortality rate of up to 30%, so this would have been a dramatic finding for the time. Meanwhile, Link and his team were already busy making new iterations of the compound and naming them with their funders' initials: WARF1, WARF2, etc. But based on animal trials, which were mostly in rabbits, none of them seemed appropriate for human use. This came around the same time that a Danish scientist had published some work on a new vitamin involved in the clotting process. Since it was needed for coagulation, it was called vitamin K. It has to do with the German spelling of the word. So Link's team wondered if this coagulation vitamin could counteract the anticoagulant effects of dicumarol, and sure enough, it did. Vitamin K worked like an antidote for dicumarol overdose. Link's lab took out a patent on behalf of WARF in April of 1945, but later that year, Link was diagnosed with tuberculosis and sent to a sanitarium for a few months of rest. According to his story in circulation, quote,
I did rest there physically for 6 months, took nothing stronger than cod liver oil and 3 bottles of beer a day, but kept the age tuberculosis out of my mind by studying laboratory records and reading the history of rodent control from ancient to modern times.
This is where he has an epiphany. If this stuff isn't good enough for humans, and we already made all these dicumarol derivatives, let's study them as rat poisons. Link got back to the lab in 1946, at which point he told one of his students to take another look at a few of the dicumarol derivatives they'd made and to report back to him. Of those, Link proposed that Warf-42 ought to make the best rodenticide. They named it Warfarin, a combination of warf and coumarin. Here's the twist, though. In 1951, after warfarin had already been on the market as a rat poison for a couple of years, an American soldier tried to kill himself by taking half a gram of warfarin a day for 5 days. But after failing his initial objective, he changed his mind. So he went to the hospital, he told the doctors what happened, and was treated with vitamin K. As the soldier's story spread, researchers started to reconsider dicumarol derivatives as anticoagulants for humans. And in 1954, an American company called Squibb got FDA approval for warfarin sodium and sold it under the trade name Coumadin. But the big, high-profile endorsement for blood thinners came in 1955 when President Eisenhower got a coronary thrombosis, which is a clot in the vessels around the heart, and was successfully treated with warfarin sodium. Which is a crazy story. Link talks about this in the circulation piece, but the drug was discovered as a cow poison, modified into a rat poison, then within 4 years was being used on the President of the United States. So over the next few years, doctors and scientists learned more about what warfarin could do clinically. An influential trial published in 1960 in The Lancet showed that anticoagulants could prevent death when used to treat pulmonary embolism in the hospital. And research in the 70s confirmed that heparin before surgery decreased the risk of fatal embolism after surgery. Soon after that, researchers learned that taking an oral anticoagulant like warfarin after venous thromboembolism reduced the patient's risk of a second one. And it was in the 1970s that scientists finally learned how warfarin worked. See, your liver uses vitamin K to make those factors involved in the clotting cascade, and thanks to certain enzymes, it can reuse the same vitamin K to keep making some of those clotting factors. Warfarin inhibits one of those enzymes, which then prevents the liver from recycling the used vitamin K. As a result, less vitamin K is available to make clotting factors, less clotting factors means less fibrin, and thus less clotting. So in the decades after it came into clinical use, warfarin became the go-to oral anticoagulant. But doctors and patients noticed an important drawback. It was really tricky to get warfarin dosing just right. Every patient's body processed warfarin a little differently thanks to the food they ate, the other drugs they took, or genetic factors. As a result, the medical team needed to monitor these patients closely and adjust dosage as needed. Now, while doctors figured out the warfarin situation, researchers were working on a better version of heparin too. They learned that only a small section of the heparin molecule actually binds to antithrombin, leading to that anticoagulation effect. So scientists wondered if they could strip everything else away and inhibit coagulation with just the parts of heparin that bound to antithrombin. This became known as low molecular weight heparin. And they worked, but through a slightly different mechanism than the old school unfractionated heparin. Low molecular weight heparin is too small to bridge thrombin to antithrombin, but it's just the right size and shape to inactivate factor XA. Low molecular weight heparin still inactivates thrombin a little bit, but it inhibits factor XA more potently. This gave the new drug some advantages over old heparin. Like, they had a longer half-life and a more predictable anticoagulant response than the old stuff. So it's not a surprise that low molecular weight heparins like enoxaparin in 1993 started to replace unfractionated heparin going forward. But there were still drawbacks. Like, low molecular weight heparin still needed to be delivered by injection. And at this point in our story, our only option for oral anticoagulants was warfarin. So scientists kept looking for alternatives that were safe, effective, and easier to use. And they would find some. But before they did, drug developers delivered a slightly different kind of oral blood thinner, one that became a blockbuster in its own right. Let's go back to 1972. Two chemists at a company called Sanofi were looking for anti-inflammatory and analgesic drugs based on compounds called thionopyridines. On the day-to-day, they'd create multiple new compounds and screen them for anti-inflammatory properties. Now, they ultimately couldn't find a good anti-inflammatory candidate, but they noticed that some of their compounds delayed clotting time in rats when given by mouth. So they made a bunch of thienopyridine compounds, and of those, they picked a drug called ticlopidine that they tested as a blood thinner, but it worked differently than the drugs we've seen so far in the video. Warfarin and heparin are anticoagulants, meaning they slow down some aspect of the clotting cascade and ultimately prevent fibrin from gluing together platelets and forming a clot. On the other hand, antiplatelets like ticlopidine or aspirin keep platelets from clumping together in the first place. Both anticoagulants and antiplatelets fall under the umbrella of blood thinners since they both prevent blood clots, just through different mechanisms. Sanofi's new drug was given the brand name Ticlid and got approval in their home country of France in 1978. Then, after it was approved, it went through more clinical testing and got approved to treat more thrombotic and cardiovascular conditions, which expanded its market potential. Unfortunately, once it was on the market, doctors noticed some rare but potentially fatal side effects. These reactions usually subsided after the patient stopped taking the drug, but they were hard to predict. So clinicians ended up being required to monitor the patient's response for at least 3 months after the patient was prescribed ticlopidine. As a result, when Ticlid was finally approved in the US in 1991, it had to come with a black box warning, and not surprisingly, it didn't sell very well. But Sanofi had prepared for something like this. While ticlopidine was in preclinical testing, the researchers had already tested over 1,000 new thienopyridine compounds with the goal of finding a drug with better efficacy and safety. And of those thousands of compounds, 8 made it to phase 1 clinical trials, and 1 was safer and more effective than ticlopidine. Then phase 2 trials showed that it effectively inhibited platelet aggregation in people who'd had clotting events in the past. But to understand what happens next, we need a little chemistry interlude. See, the 3D shape of a drug can make a big difference in a drug's effectiveness, and some molecules have something called chirality. There are left-handed versions and right-handed versions called enantiomers of that molecule. These are versions of the molecule that have the same pieces, but they're mirrored, not identical. But sometimes one of the enantiomers makes for a more potent drug than the other. For example, the S enantiomer of ibuprofen is more potent than the R version, although some of the R ibuprofen is converted to S in our bodies anyway. Sanofi's new antiplatelet candidate was a mix of both S and R enantiomers. But because they ran into unexpected side effects with Ticlid, they decided to test each enantiomer separately to see if one was safer than the other. And when they did, they found that the S version was active, while the R version was inactive. They called the S enantiomer clopidogrel, and got a patent on it in 1982. Then they started preclinical testing starting in 1987, and by 1993, they'd made it to phase 3 testing. But Sanofi needed some help marketing and distributing the drug internationally, especially in the US. So they decided they'd co-market the drug with Bristol Myers Squibb, at the time, the 4th biggest drug company in the world. They'd finished developing clopidogrel together and split the remainder of development costs 50-50. The drug was approved in November of 1997 for the reduction of events like heart attacks and strokes in patients who'd had one before or who had a specific vascular disease. They launched the next year under the brand name Plavix in the US and Discover in Europe. And medical professionals took to clopidogrel quickly. Surgeons started using it in surgery, and some doctors started preferring it as an antiplatelet over aspirin because it didn't have the same side effects on the GI system. This caused Plavix to hit blockbuster status after just a few years. By 2011, it earned over $7 billion in global sales for BMS, and over $42 billion for them in the drug's lifetime. The clopidogrel patent expired in 2012, at which point the FDA started approving less expensive generics, and Plavix sales fell off. Now, it was great to have a new blood thinner available, but healthcare providers and patients still needed something more. According to a 2012 article published in The Lancet, thrombosis diseases like heart attacks, strokes, and VTE killed 1 in 5 globally in the 1990s, but rose to 1 in 4 globally by 2010. Throughout the 90s, though, studies showed that warfarin could reduce the risk of strokes in patients with non-valvular AFib, meaning atrial fibrillation not caused by valve issues. And that was good to know considering the number of people in the US living with AFib was on the rise. It's still very common today. This led to more doctors prescribing warfarin for this new indication. But warfarin still had its shortcomings: the drug-drug interactions, the constant dose adjustments, and a risk of excess bleeding. Meanwhile, even the newish low molecular weight heparins required injections. So by the early 2000s, there was demand for a new blood thinner. Ideally, an oral drug that could be more standardized and didn't require such tight monitoring. And by the 2010s, doctors didn't just get one drug that met those standards, they got 3. This is Hirudo medicinalis, otherwise known as the European medicinal leech. Old school healers used to use them to bleed their patients and balance their humors, back when that was popular. One of the reasons these leeches can suck blood in the first place is because there's a natural anticoagulant in their saliva called hirudin, named after their genus, Hirudo. Hirudin binds to thrombin where thrombin would otherwise bind to fibrinogen, which prevents it from turning into fibrin and causing a clot. Scientists found the amino acid structure of hirudin back in the 70s, which allowed chemists to make a modified version of the protein using recombinant DNA, then smaller versions containing only the active binding sites. This short synthetic portion became known as bivalirudin, and it became the first in a class of drugs called direct thrombin inhibitors. But it was still injection only, so the pharma company AstraZeneca tried finding an oral version of hirudin. They developed enogatran in the mid-80s, and while the injected version worked well, it had super low bioavailability when taken orally, and that became the big challenge. Drug developers wanted to figure out how to get more of the compound from the gut into the bloodstream, and this led to a dipeptide drug called malagatran. It was smaller and more potent, which would theoretically let it survive digestion, but when it was tested in real human bodies, it wasn't super bioavailable when taken by mouth. So AstraZeneca scientists created a prodrug called xymalagatran. A prodrug is inactive on its own, but gets metabolized by the body into an active form. In this case, xymalagatran would cross from the gut into the bloodstream and then shapeshift into malagatran. Clinical trials looked good at first. It prevented venous thromboembolisms, strokes, and cardiovascular events in certain high-risk groups better than a placebo. The results led to the drug's approval in Europe and sale as Xanta. Unfortunately, that was followed up with reports of liver toxicity. So in 2006, AstraZeneca withdrew the drug from the market. The FDA never approved the drug in the first place, so xymalagatran was never sold in the US. Either way, the story showed that a new generation of oral anticoagulants were at least possible. The story culminated in October of 2010, when a German company called Boehringer Ingelheim got FDA approval for their new direct thrombin inhibitor, dabigatran, making it the first FDA-approved oral anticoagulant since Warfarin back in the 1950s. They sold it under the brand name Pradaxa, and like Warfarin, it was approved for the prevention of stroke in patients with AFib not caused by valve issues. But it didn't require the constant monitoring like Warfarin did, so dabigatran quickly took a chunk out of the anticoagulant market. According to a 2012 article, doctors wrote about 8.8 million Warfarin prescriptions each quarter from 2007 through 2010. But in Pradaxa's first year on the market, it jumped from 73,000 prescriptions a quarter to 733,000, making them about 8.1% of the anticoagulant market at the time. The numbers were even more drastic when you look at healthcare spending. By the end of 2011, America spent more on dabigatran than on Warfarin. But Boehringer Ingelheim wasn't the only pharma company to take advantage of a growing demand for anticoagulants. One of the other promising targets in the clotting cascade was activated factor 10, or just FXa. This is the enzyme that catalyzes prothrombin into thrombin. Researchers liked it as a target for two big reasons. First, a single molecule of factor XA creates hundreds more molecules of thrombin, so inhibiting FXA should be more efficient than targeting thrombin directly. Second, unlike direct thrombin inhibitors, FXA inhibitors wouldn't affect the thrombin that's already been made. That would allow patients to retain some clotting ability and hopefully not have to deal with unexpected bleeding events. Researchers at Bayer in Germany started exploring potential factor XA inhibitors in 1998 and published their findings on a new drug called rivaroxaban in 2005. Fun fact, most factor XA inhibitors end in XA-ban, which I remember because it's like the drug bans factor XA. European regulators approved rivaroxaban in 2008 for the prevention of blood clots after knee and hip replacements. But to enter the US market, Bayer decided to partner with Johnson & Johnson. Here, they launched rivaroxaban under the brand name Xarelto in August of 2011. Meanwhile, Bristol Myers Squibb, the same company who brought Plavix to the US, was developing its own oral FXA inhibitor. Their goal was a drug with a half-life that would allow for twice-a-day dosing at most, plus minimal swings between high concentrations and low concentrations. Some of their first compounds inhibited factor XA, but didn't cross from the digestive tract into circulation well, which defeated the purpose of an oral drug. So they looked for new molecular structures, prioritizing absorption from the gut, along with a strong binding to factor XA. And that led them to apixaban, an FXA inhibitor that checked all their preclinical boxes. Good absorption from the gut, low likelihood of drug-drug interactions, and low risk of excessive bleeding. They filed a patent for it in September of 2005, then apixaban went on to clinical trials. During phase 3 clinical trials in 2007, Bristol Myers Squibb announced that, pending FDA approval, they would co-market apixaban through a partnership with Pfizer. As part of the deal, Pfizer would pay BMS $250,000 up front, then they'd split development and marketing costs going forward. Now, Pfizer was enjoying the financial success of their blockbuster statin Lipitor, but its patent was set to expire in 2011, so they needed something new in their pipeline. Something like apixaban. In return for sharing apixaban, BMS would benefit from the size of Pfizer's massive sales and marketing team. At the end of 2012, the FDA approved apixaban for, quote, reduction of risk of stroke and systemic embolism in non-valvular atrial fibrillation. Pfizer and BMS launched it under the brand name Eliquis. Then in 2014, the FDA approved Eliquis for the prevention of DVT after major surgeries. For those keeping score at home, yes, the FDA approved 3 new oral anticoagulants within 2.5 years. There was dabigatran in October of 2010, rivaroxaban in 2011, and apixaban in December of 2012. But that begged the question, what do we call these new drugs? They've actually gone by a few names over the years, including NOACs for novel oral anticoagulants or non-vitamin K oral anticoagulants. But these days, on recommendation from the International Society of Thrombosis and Hemostasis, they're called DOACs for direct oral anticoagulants. This term includes drugs that directly inhibit thrombin, like dabigatran, or directly inhibit factor XA, like rivaroxaban and apixaban. And one of the most convenient aspects about these new DOACs was that patients didn't need the constant monitoring like they did on Warfarin. Instead, they got a more convenient and consistent dose, which made patients more likely to keep taking them. But there was still a problem. People who took DOACs still had risk of excessive bleeding. And Warfarin carried a similar risk, but at least there was an antidote with vitamin K. And in 2012, there wasn't an antidote for any of the DOACs yet. Pradaxa's parent company eventually got approval for its antidote at the end of 2015, but the others would have to keep on looking for a few years. Now, for reference, before Xarelto and Eliquis came out, the American anticoagulant market was worth about $10 billion, mostly from the sale of Warfarin and that new thrombin inhibitor, Pradaxa. By 2015, Xarelto by itself brought in 2.25 billion euros for Bayer. But Eliquis started catching up after only about 2 years. There were a few reasons for that. First, some studies came out that made it seem like Eliquis was the safer choice. But before getting into those studies, now's a good time to remind you that none of my content is medical advice, and you should talk to a healthcare professional before making decisions about medications. Back to the story. In 2016, a report in JAMA Internal Medicine compared the safety of dabigatran to rivaroxaban among Medicare recipients who took either drug to prevent strokes. The authors concluded that rivaroxaban users had a greater risk of brain bleeds than the dabigatran users. A similar study compared all 3 new DOACs to Warfarin and reached similar conclusions. According to their analysis of Medicare Advantage enrollees with non-valvular AFib, rivaroxaban use was associated with about the same risk of stroke and excessive bleeding as Warfarin, while apixaban use was associated with a lower risk of stroke and excessive bleeding than Warfarin, making it seem like a safer and more effective choice. The second reason that Eliquis passed Xarelto was pure marketing. While both pairs of companies led direct-to-consumer campaigns in the US, BMS and Pfizer straight up outspent J&J and Bayer. This led to the first quarter of 2017 when Eliquis became the most prescribed DOAC in the United States, and the profits followed. Eliquis generated $1.86 billion in revenue for Bristol Myers Squibb in 2015, then $3.3 billion in 2016, and $4.87 billion in 2017. And clearly, it's taking market share away from Warfarin. In 2015, Warfarin was 62% of the oral anticoagulant market, but by 2016, it was down to only 55%. Then in May of 2018, a company here in the San Francisco area called Portola Pharmaceuticals came out with Endexa, an antidote for Xarelto and Eliquis. This gave the 2 blood thinners a little sales boost, and by the end of 2018, Eliquis passed Warfarin as the most prescribed oral anticoagulant in the US, generating $6.4 billion for BMS in the process that year. But that revenue comes from paying customers, and one of their customers happened to be the United States government. See, these drugs are so common with patients over 65 that they represent a significant percentage of Medicare spending. For non-Americans, Medicare is our federally sponsored health insurance program, but it's mostly for the elderly, plus some younger folks with disabilities. According to a 2024 study from researchers at Penn State and the University of Virginia, Eliquis was the most frequently prescribed drug for Medicare beneficiaries, as well as Medicare's biggest brand name drug spend at $4.1 billion from 2017 to 2019. It represented 2.8% of Medicare's prescription drug spending. Xarelto was up there too, costing Medicare $2.4 billion in the same timeframe. So the government decided to do something about it. In 2022, President Biden signed the Inflation Reduction Act, which allowed Medicare to negotiate prices for certain high-cost drugs that didn't yet have generic competition. Medicare started the negotiation process in early 2024, and the new negotiated prices will take effect in 2026, including new prices for Eliquis and Xarelto. The US has tried to bring down drug prices before, but it's usually been through market incentives like speeding up the generic approval process. And legislators have tried to introduce laws that limit drug prices, but they've mostly failed or had a narrow scope, like the 340B program for certain healthcare providers. I personally imagine this part of the Inflation Reduction Act like the US dipping their toes into the price control waters. Medicare can negotiate prices for a few drugs for now, but only some of the most expensive ones that don't have generic or biosimilar competition. These drugs also must have been on the market for at least 9 years for small molecules or 13 years for biologics. And this kind of negotiation power is possible because Medicare is one of the biggest customers for these drug companies. While pharmaceutical companies weren't exactly excited for price reductions, they didn't want to lose access to billions in Medicare revenue. Speaking of revenue, after the negotiated prices were announced, BMS released a statement to investors saying they still expected Eliquis to earn the company anywhere from $8 to $10 billion a year through 2027. That would be down from their peak of $13.3 billion in 2024, or whatever they make in 2025, but still a massive blockbuster. Afterwards, the price of Eliquis will come down when their patent finally expires, which is another story. Thanks to a legal battle between some generics producers and BMS, there won't be a generic apixaban until 2028 at the earliest. I couldn't find any info on the FDA's website about this story, so most of my sources here are BMS press releases, which obviously carries its own bias. Xarelto's patent expiration was more straightforward. There's a tablet version and an oral suspension version of rivaroxaban, and the last patent for the tablet expired in May of 2025. As a result, the FDA approved a generic 2.5 milligram rivaroxaban in March of this year. So, what's the takeaway? What can we learn from all this? Well, starting with the ongoing story, Eliquis and Xarelto's financial success was so unique that the federal government got involved. Now, the ethics of drug pricing aside, it's clear to see why the DOACs made so much money. They solved the problem. The constant monitoring on warfarin was a huge hassle for patients. So when these new blood thinners provided an alternative, doctors wrote tons of prescriptions for them. But the combination of high prices and a large market caught Medicare's attention. So in some ways, they're victims of their own success. Again, I'm not exactly feeling sorry for them. My second takeaway is that serendipity has a role in drug discovery. Professor Link didn't set out to discover warfarin. The catalyst for the discovery literally showed up at his doorstep with a jug of cow's blood and moldy hay. And decades later, it took a soldier's suicide attempt to give warfarin another look as a blood thinner. Scientists might have never revisited warfarin as a therapeutic if such a dramatic story hadn't reintroduced them to the idea. And actually, speaking of dramatic stories, I've got a documentary recommendation for you. It's called 17 Pages, a feature-length documentary that follows the story of a paper published in Cell in 1986 and how it led to multiple investigations of academic fraud. Some of the details of the trial depend on understanding some complex immunology, but the man behind the doc, Kevin McKay, otherwise known as Bobby Broccoli on YouTube, did an incredible job of explaining the science while progressing the story. It's the same thing I tried to do with my videos, but he executes it so beautifully with such a distinct style. You can watch the documentary exclusively on Nebula, the sponsor of this video. Nebula is an indie streaming service made by creators for creators. I post all my videos there early and ad-free before you can see them on YouTube, but Nebula is also home to over 200 creators now, including some of your favorite in the health space like Chubby Emu, Midlife Crisis, therapist Georgia Dow, and cosmetics expert Lab Muffin Beauty Science. Plus, there are tons of Nebula originals, series and documentaries that you won't find anywhere else. Like Tom Nicholas has a great doc called Boomers, where he travels to the US to look at the impact of the baby boomer generation. But what I love most is the curation. Nebula's created a space where everything on there is high quality. I spend most of my video watching time these days on Nebula, and I'm always impressed by the creators I'm discovering on the platform. So if you want to check out Nebula, go to go.nebula.tv/Patrick Kelly to learn more. And if you use my link, you'll get 40% off an annual subscription, which brings it to just $36 for a full year. That subscription directly supports my work, as well as the production of interesting new content. Again, that's go.nebula.tv/Patrick Kelly, or you can scan this QR code. Thanks for watching, y'all. Take care.